Hello again, and welcome back to the second installment of my video series, in which I aim to describe some of the fundamental supervised learning models that can be used for parameter estimation in the physical layer of wireless communication systems. Like in my first video, discussing the convolutional neural network, this video is inspired by a paper written by Mcclintick et al. This paper provides a very thorough guide to the application of supervised learning techniques for the purpose of facilitating rapid improvement of wireless communication systems in ever-changing or even unknown channel conditions. I would like to start again by showing this table of some of the most commonly used models for this application. As you can see, there are many. However, today I will be focused exclusively on the k-nearest neighbor model. So let's jump right in. I will start by covering the fundamentals, or the basis of the model. Then I plan to go into a bit more detail about how this model can be applied to different types of parameter estimation problems. From there, we'll jump into how best to cater the k-nearest neighbor model to your unique application. So let's begin with some of the basics. The k-nearest neighbor model is a non-parametric supervised learning classifier that is based on the principle that data of the same type will be found in close proximity. This model is most often used for two distinct types of problems, the first being classification and the second being regression. So what is the difference? And how does this apply to channel parameter estimation? For classification problems, the k-nearest neighbor employs the use of what is referred to as plurality voting, or sometimes majority voting. This is done in order to determine which class a particular data point belongs to. To go into a little bit more detail on this, let's imagine that we have collected an arbitrary number of data points. Now let's say we want to classify these points into two separate classes. In this case, this would be defined as a classification problem. In the k-nearest neighbor model, the distance between all of the collected points would be calculated. With the distance between the points now known, the two classes can be defined based on the grouping of the points collected. We can picture an imaginary line between the two groups that can act as a separation point, or the point at which one class becomes another. When evaluating an individual data point, we call this point the query point. This point would be considered of class A if it is closer in proximity to the other points of class A than those in class B. In other words, the point would be of class A if it is on the side of this line that has been identified as class A. If this is not the case, the opposite is true, and the point will be of class B. Regression problems are approached in a very similar way when using the k-nearest neighbor model. The main difference is that in regression problems, the data that is to be classified is continuous instead of discrete. This means that the k-nearest neighbor model is useful only in forming a prediction about what the classification of points will be. Due to the continuous nature of the input data, the average of the k-nearest neighbors is taken in order to formulate a classification prediction. In terms of channel parameter estimation, this is a far more realistic scenario. This is because supervised learning models, such as this one, are often employed when communication needs to occur across an ever-changing channel and operating conditions. It is important to note that unlike other supervised learning models, this model is not retrained iteratively. Instead, the training data is stored and referred to every time the model conducts a classification. In the context of the example that we just discussed, the training data would be the distribution of points that led to the initial drawing of that class boundary. Whether the channel parameter estimation problem is a classification problem, or more likely, in the context of wireless communication systems, a regression problem, the first step in applying the k-nearest model is to calculate the distance between the data point being classified and the training data. So, how might we go about calculating this distance? There are many different distance calculations that are compatible with the k-nearest neighbor model. For example, there is the Euclidean distance, the Manhattan distance, Minkowski distance, and even Hamming distance. However, depending on the parameter estimation problem at hand, one method of distance calculation may be more advantageous than another. For example, Euclidean distance can only be used if that data that is being classified are real valued vectors. The Manhattan distance doesn't share this restriction. However, it works by finding the absolute value between the points in question. The Minkowski distance is very similar to the Euclidean distance. However, in this case, p is not equal to 2. This has the effect of allowing for the addition of different distance metrics. Lastly, we have the Hamming distance, which is best used only in the case that the data is Boolean. The method of calculating distance that should be selected is completely dependent on the type of the data being classified in your given parameter estimation problem. Now, this supervised learning model is called the k-nearest neighbor. At this point, you may be wondering, what is k? Well, the answer to this question is quite simple. K refers to the number of neighbors, or nearby data points, that need to be checked in order to confirm the classification of the query point. If K of the neighboring points within a calculated distance have the same classification, let's just say class A, then the query point will also be a part of class A. This value K is user selected and can be any number from 1 to the number of data points that exist. Selecting the value of K for a given parameter estimation problem can be challenging. This is because if K is too large, you might be overfitting the data. This would result in high bias and low variance. However, if K is too small, you run the issue of underfitting the data. This has the opposite effect, leading to low bias but high variance. Ultimately, like the method of calculating distance that should be used, the value of K that should be used is completely dependent on the type and quantity of data being classified. However, there are some basic rules of thumb that might help to restrict the value K can be. It is known that the more variability in the data, the higher the value of K should be. This means that if the data being classified, in terms of wireless communication, is very noisy, a higher value of K would be ideal. It is more likely than not that there will be noise present within a real-life communication channel. Because of this, higher values of K should be used for the majority of parameter estimation problems that pertain to the physical layer of wireless communication systems. In addition to this, it is recommended that K be an odd number. This is because when K is odd, it rules out the possibility that a particular query point falls between more than one class. This would occur if the same number of neighboring points were of, let's say, class A, as they are of class B. As it can be seen here, if k is equal to 4, there are an equal number of data points of class A and of class B. However, if k is equal to 3, the query point can easily be identified as of class B. If you're interested in learning about more supervised learning algorithms like this one, I highly suggest you take a look at my other videos. I hope that this video was helpful, and if you have any questions, I recommend taking a look at some of the references I have linked in the description below.